Good morning, everybody, and welcome to the third and final day of the Digital Day in the Park. Before we get started with our wonderful speakers today, we're going to take a few minutes to hear from our hosts. First, you'll see a welcome video from Greg Blaney, the director of the NASA Katherine Johnson Independent Verification and Validation Program, followed immediately by a welcome from Dr. Mirta Martin, the president of Fairmont State University. We'll be back in just a few minutes.
Hello, everyone. My name is Gregory Blaney. I am the director of NASA's Independent Verification and Validation Program located in Fairmont, West Virginia at the Katherine Johnson IV&V facility. And I welcome you to this virtual Day in the Park event. First, let me talk about all the changes and challenges this COVID pandemic has brought to our lives. Yes, there has been significant changes and challenges, but I encourage you to look for the benefits and opportunities that came about due to the pandemic. I know that I've been experiencing and learning new ways of doing things. I've learned how to use new communication tools. I've learned that our employees can adapt and work from almost anywhere. And because NASA's been forced to move to more of a virtual operations for STEM engagement, like this one, we have actually been able to reach more people in more places. Therefore, I encourage all of you to focus on the new things you are learning to do and capitalize on them after this pandemic is over. In addition, one of the biggest things I believe we have all learned is that we can adapt and overcome. Let me talk just a moment about why I highly support NASA and Fairmont State University conducting events like this. I want every one of you students to know that you can be successful and secure a good job wherever you want to live. And one way to make that happen is to pursue a career in a STEM field. Obviously, STEM stands for science, technology, engineering, and mathematics. Moreover, you can work for NASA and many other exciting places right here in West Virginia. If you do not believe me when I can say you can work for NASA or another government agency or a great company here in West Virginia, let me tell you a little bit about myself. I was born in Morgantown, West Virginia, and lived just across the state line out in the country between Point Marion and Smithfield, Pennsylvania. I grew up working on my grandfather's farm and doing carpentry work with my father. I did okay in school, but not really apply myself as I should have. I was more interested in playing football. However, events in my life provided me an opportunity to work for the Bendix Field Engineering Corporation at the Goddard Space Flight Center in Maryland. I started at the very bottom of the ladder because I did not have a college degree or much experience. However, I quickly learned that you could advance your own career through hard work and furthering your education. So over the past 40 years, I've gotten to the place where I get to work on NASA's most important missions. I get to see NASA launches. I travel to other NASA centers and get to see what they do there. And my boss is an astronaut. Yes, he's flown in space 4 different times. Actually, I've gotten to work with and become friends with several astronauts. So instead of waiting until you are older, as I did, decide to work a little harder in school. Get a good college education. Find a career you really like, and then do great work for whomever you work for. In addition, do not forget, you can be flexible with your career. Do not be afraid to change or adapt to new things. Lastly, STEM fields are involved in almost all careers these days. In fact, almost all STEM fields are needed in NASA. If you're interested in aerospace, space science, robotics, computer science, software engineering, cybersecurity, energy, or climate, we need you in NASA. So I hope you enjoy this virtual event. I hope that it inspires you to do your best in school. I hope you pursue a career in a STEM field. And I hope we see you working for NASA someday. Have fun, have a great event, and thank you.
Hello, I'm Dr. Mirta Martin, President of Fairmont State University. Welcome home. I hope that you're enjoying learning about STEM fields and careers today. There really has never been a better time to explore an interest in the STEM fields. Whether you're interested in robotics, aeronautics, and aviation, computer science, energy, or climate studies, STEM fields are constantly forging new paths and innovating. It will be future STEM professionals, just like you, who help solve some of the greatest challenges and shape the future of our humanity. If you're interested in pursuing a career in a STEM field, Fairmont State is your destination, whether you want to jump into a STEM career or go into graduate study. We have several academic programs across the entire spectrum of science, technology, engineering, and mathematics. Our state has so many bright students, just like you, who are interested in STEM fields, and we need you. And so I want to take a few minutes to talk to you about our programs, because we have some very special programs. Some of them are even the only ones of their kinds in our state. A STEM program, for example, that is unique to Fairmont State is our aviation program. It's our flagship program. If you've looked up in the sky and you have seen a maroon and white single-engine plane, chances are that that's a Fairmont State aviation student logging flight time. We offer the only FAA 141 flight school program in the state. You can also study non-flight options like management, air traffic control, and security. Fairmont State also only has the only undergraduate and graduate architecture program in the state. Architecture is a unique STEM field that combines art and science, and it is an exciting career for creative thinkers. Yet another field that combines creativity, art, and science is graphic design technology. You'll not only take courses in art, in design theory, 2D and 3D design, and concepts of photography, but you'll also take tech courses like computer technology. Upon graduation, graphic design technology students might find rewarding careers as graphic designers, web designers, technical illustrators, or desktop publishing artists. Our computer science programs have been specifically designed so our graduates can find employment in a variety of sectors. You can study to become a computer programmer, systems analyst, software engineer, or even work in cybersecurity. You might also choose to continue your interest in biology or perhaps chemistry. Fairmont State University has the latest cutting-edge scientific instrumentation and equipment, and you'll love it. And the great thing about studying biology or chemistry at Fairmont State is that you get to actually use the equipment, even just at the beginning of your academic career. At many other larger schools, you'll have to kind of wait your turn. Not so here. It's hands-on, no waiting. Another program where you get to use sophisticated equipment is forensics. While forensic scientists are the stars of many hit television shows, the career options are vast. Students often combine their forensic science degree with their love of chemistry, with their love of biology. Forensic science graduates who go directly into the workforce often enjoy careers as medical examiners, criminologists, forensic anthropologists, forensic chemists, forensic pathologists, and yes, even toxicologists. Now let's talk about mathematics. Mathematics graduates have a world of career opportunities. Education, finance, manufacturing, cryptology, biomathematics. I can go on. Math professionals constantly break new ground and innovate every single field. A degree in one of these 3 engineering programs that we have here at Fairmont State makes use of your love of math and also of science. For example, civil engineering technology prepares you for a career where you plan, design, and build things like roads, airports, tunnels, and bridges. Electronics engineering technology prepares graduates to work in a wide variety of industries. They make or use electrical and electronic equipment like communication systems, microcontrollers, advanced linear electronics, and advanced automation systems. Mechanical engineering technology students have fun, hands-on learning experiences. For instance, they design, they fabricate, test, and complete race cars, robots, and industrial designs at the nation's top engineering campuses. And after you graduate, you might go on to a lucrative career as data analyst engineers, or perhaps even a project engineer. Another field that is housed in the Department of Engineering Technology is our occupational safety. This is an important field that makes sure that public and workspaces are safe. Upon graduation, you might find a career as an occupational health and safety technician, agricultural inspector, fire inspector, or even a building inspector. And oh, by the way, Fairmont State has the only occupational safety program in our state. In addition to our excellent STEM academic programs, we offer dozens of activities and events for students interested in STEM. One of those is the West Virginia Brigade of the Solar Army, a global organization dedicated to harnessing the sun's energy to make renewables fuel. There are activities that you can get involved in right now, and it's important that you do so. For instance, our online virtual math, science, and energy fair take place here in January and February. You could also get involved with Skills USA, a national technology competition, or First Lego League, and your school's science fair. So you ask me, why is it important that you keep involved in STEM classes and in STEM activities? Because you are the future of West Virginia. West Virginia, as well as the entire world, faces many challenges, and it will be up to students just like you, interested in STEM fields, to find the solutions that ails our planet. You are a generation of innovators, of problem solvers. You can turn your interests in STEM subjects to make West Virginia and the whole world a better place. I've given you a little bit of background at Fairmont State University, and I so hope and pray that you enjoy the rest of your virtual day in the park. I invite you to explore our STEM programs and activities at fairmontstate.edu/STEM. Welcome home to Fairmont State. We are so thrilled that you are joining us today, and I look forward to seeing you very soon right here as one of our students. God bless you.
Welcome to the third and final day of Day in the Park. We have some fantastic presenters this morning who are going to be talking about energy. If you'd like to check out our website for some extra resources, it's in the description below. And there's also a link to our questions form where you can ask questions of the presenters. We have some equally fantastic presenters this afternoon for our climate session, so we hope you stay around for that. But I would like to introduce our keynote speaker this morning, Dr. Brian Anderson. He is the director of the National Energy Technology Laboratory. He's a West Virginia native, originally from Ripley in Jackson County, and his first experience with NETL was through the Science Bowl in high school. He attended West Virginia University and then came back there to teach, where he also founded the WVU Energy Institute. So without further ado, thank you for being here this morning, Dr. Brian Anderson.
Well, Emily, thank you so much for the introduction. I really appreciate having an opportunity to talk today about something that is certainly very near and dear to my heart, and that's energy. And, one may ask, what is energy? And a realistic answer is energy is everything. Energy is everywhere. It is a constant in the universe. As long as there's been a universe, as long as there will be a universe, there will be energy. And it comes in lots of different forms that seem different to us, but they're really the same thing. Energy is the ability to do work, and work is the act of displacing something by applying a force. Say you throw a frisbee or a boomerang. The force of your hand is turned into the force of flying disc that's now pushing through the air around it. Or maybe you're in Fairmont near the Katherine Johnson IV&V facility and you're enjoying a nice patty melt at a place called the Pokey Dot. The energy from that food is broken down into energy for the quadrillions of cells that you have that do all sorts of things that they have to do. They make copies of your DNA, they assemble, they repair proteins, they transport materials from a place to another, they make your muscle cells contract, the stuff that's being alive. Then the food turns into carbon dioxide and you breathe it out. The boomerang that sails through the air, the cells that are toiling away, your phone or computer right now that you're watching, that's all work being done. In the computer, it's moving digits around. The last week I was camping at Babcock State Park, and if anybody is familiar with West Virginia, the leaves haven't quite turned yet, but they're just about to. And we were walking around and found a dry log. Now, we think about that dry log. For 1 million years, humans have been using energy to make our lives easier. About 300,000 years ago, we know that they were using flint to start fires from those dry logs. And it's because the chemical energy that's made up of the combinations of carbon and hydrogen and oxygen that's all formed into the lignin and the lignocellulosic material inside of that biomass, and I'll talk a little bit about this later, that's the stuff that makes up wood. And all those chemical bonds between the atoms contain energy. So if you apply a little extra energy, the spark from the flint 300,000 years ago, or a lighter, that heat then starts to break down the bonds and releases chemical energy as fire, and then it keeps going. It releases more energy with more energy. And so that chemical energy in the wood is the same that you get from the patty melt. It's that chemical, when we break those chemical bonds, we can create energy. But also, if you look inside the atoms that make up the patty melt or the log, it contains nuclear energy. Each atom inside has a nucleus, it has protons and neutrons, it has electrons that are surrounding it, an electron cloud. The energy that's holding them together is one of the most powerful sources of energy in the universe. So if we look at atoms that are making up anything, there's nuclear energy that's locked up in it, and you can release it through nuclear reactions and create power. And so as it turns out, the matter that makes up the log and the energy are actually very similar to the same thing. You've probably heard of the equation that a German patent clerk named Albert Einstein came up with about 100 years ago. E equals mc squared. Energy is mass times the speed of light squared. There are so many types of energy that I'm going to talk about here over the next few minutes. And there is a mysterious form of energy called dark energy. I'll ask the folks at NASA to explain what happens, what dark energy is, and how it is in fact making the universe expand faster than it should. And in our universe, and perhaps if somebody can explain what's in the center of a black hole, maybe another universe, but in our universe, energy is critical to everything we do. And so I'm gonna share some slides with you today and talk about what we actually I need the host to enable screen sharing for me. And so I want to talk about what we do at the Department of Energy. I actually defined energy as what? Everything and everywhere. The former Department of Energy liked to say it was the Department of Everything. We do have research that's ongoing in all aspects of our daily lives. And so if I don't know who's the host, if I can get screen sharing up. If not, I'll just
we'll make sure that is taken care of right away.
Okay, just let me know when, and I can keep talking.
We have a question already from Preston, who asks, why is energy so important to us? And I think you've touched on that a little, but if you just want to.
But Preston, it's absolutely a great question, because energy is what turns our lights on. It's what keeps us warm at night. It's what helps us move from place to place in cars and airplanes and trains. But actually, it's what has made life so much better than it was 1,000,000 years ago or 300,000 years ago, because our access to low-cost, reliable energy has lengthened our lifespan. If you go into the communities around the globe, there are 7 billion people on the planet. There are about 1 billion of those 7 billion people on the planet that don't have regular access on a daily basis to reliable energy, not even to mention clean energy. And that billion people, their life expectancy is considerably shorter than those of us who live in the United States with access to regular, reliable, clean energy and clean air. And so I think that it's important to us because it has enabled us to focus our lives not on gathering firewood and not on hunting and gathering, but energy has enabled our lives to be much simpler and enabled technology and the development of drugs that can help our lives move forward. I was going to, still don't have screen sharing, just as a check, but I was going to mention that the Department of Energy is the Department of everything, because we study everything from the fundamental science of how atoms are bonded together and even subatomic particles at our sister laboratories across the Department of Energy complex with the world's greatest particle accelerators and X-ray synchrotrons. We have been able to describe the interaction of molecules at such a level that much of the vaccine design and analysis of the COVID pandemic today has been going on in the Department of Energy through something called the National Virtual Biotechnology Laboratory that we assembled back in February. And so we have been working on computational work to try to design new drugs for the treatment of coronavirus, as well as many other diseases. It was the Department of Energy that, in fact, performed the Human Genome Project. Just 2 days ago, one of our sister laboratories, the Lawrence Berkeley National Laboratory, one of the scientists there was awarded the Nobel Prize in Chemistry for developing gene cutting and gene splicing technologies that are leading to future health outcomes that will be really changing the world. I still don't have a screen listing.
Okay, I think we know what we need to do, and I apologize for the delay. If you'll leave the breakout room, we can make you a co-host, and then you can come back in. So I will be ready for you when you get back.
All right, I'll leave the room. I hope I can come back. See you soon.
All right, well, I can share my screen. So I'm just going to walk you through how to get to our website, because that is where this whole conference will still be hosted when we are past Day in the Park. This is going to be a durable resource that educators and others can come back to. And so I'm just going to kind of talk you through how to get to our site. Like I said, it's linked below. Oh, how are we doing, Brian?
I can share.
Right. Well, to heck with that website. You know where the URL is. Go and check it out when you have a moment. And Brian, thank you so much for getting through that hiccup.
Oh, that's all right. We're adaptable and we have fun.
Absolutely.
I hope if anybody out there takes one thing home today and said, I'm excited to talk about energy and could do it all day. But I only have a limited amount of time. So I'm going to talk, specifically about some of the energy technologies that are coming down the pipe for us as a nation, as a globe, to tackle some of our greatest energy challenges, because nothing in life is free. And so there are challenges that come with the way that we have produced energy for the last 300,000 years, and especially the last 200 years in terms of our usage of energy that emits carbon dioxide and the global challenge of climate change that you'll hear about this afternoon. And so we at NETL have been working on technologies for energy for the last 100 years. 110 years, as a matter of fact. We were founded in 1910, and we're driven by some global drivers. And the global drivers, I talked about the human population that's growing. We're at 7 billion today. And in fact, not only the billion people that don't have access to regular, reliable electricity or energy on a daily basis, the growing population is growing in areas that don't have all that great access to reliable and clean energy. And certainly, as we grow the population on the earth, food becomes a problem, clean water becomes a problem, and energy becomes a problem. And the three of these, food, water, and energy, are integrated so much that you cannot take them apart. We use water to make energy. As a matter of fact, in the United States, more water is used to make energy than any other industry combined. And that's because we use it to cool because of something called the second law of thermodynamics that states that you cannot convert all energy into electricity. There's a limit there. And then when it comes to food, food production is energy intensive, but it's also, there are opportunities as we drive down the cost of clean energy, the opportunity then to create more plentiful food in new growing environments. So some fun facts about the Department of Energy is we did in fact reveal the dinosaur killer. We brought the internet to the United States. We enable space exploration. As a matter of fact, the most recent Mars mission was a partnership between NASA and the Department of Energy in terms of the propulsion and energy systems on board space exploration. And we're working on tomorrow's technologies for how we can harness energy in remote environments, say on the moon or on Mars, to enable deep space exploration. And we put the digital part in DVDs, so we're working lasers and digitization. The Department of Energy is not just a government agency, but 17 Department of Energy national laboratories across the United States. There's about 100,000 scientists as part of the Department of Energy laboratory complex. As you can see, if you look for NETL, you can find us in West Virginia. You can find us in Pennsylvania at our laboratory in Pittsburgh. Our lab in West Virginia is in Morgantown. And in Oregon, it's in a town called Albany, Oregon, that's close to Oregon State University. And we partner with these other 16 national laboratories on a daily basis to try to solve some of the world's greatest scientific challenges. We are, by stewardship, the fossil energy laboratory, because we've been working on reducing the environmental risk and the human capital risk of fossil energy generation for the last 110 years. A couple other laboratories to point out is one is the National Renewable Energy Laboratory in the Idaho National Laboratory. NREL, the Renewable Laboratory in Colorado, is a sister lab to us, and we're partnered on all kinds of different projects across the energy space. Well, where does our energy come from today? The energy that we use in our homes and our cars and our buses and our airplanes, 80% of it today is coming from fossil energy. And as you see, if you look on the right side, 93% of the energy used in homes and in commercial businesses comes from fossil energy. It's because natural gas is so easy to heat our homes with. When we look at the transportation sector, 95% of our transportation sector energy comes from fossil energy. I bet you if I had the opportunity to ask you where you thought it came from, you would know it comes from oil, and it's oil turns into the gasoline that we use in our cars. And there's a huge challenge for us because when we eat the patty melt and we convert the chemical energy into useful energy to move our muscles, it's just exactly what happens in the car. We burn gasoline in the car and we produce carbon dioxide and water, and it's coming out of the tailpipes of every car on the road. So we need to be able to centralize that through electrification, through using alternative fuels and ways to reduce our carbon footprint. Right now, the transportation sector out-emits the power sector in terms of carbon dioxide, and that's really due to natural gas lowering the carbon footprint of the power sector, in addition to wind and solar that's on the grid. So I want to talk about a few of the energy sources. Biomass, I've been talking about. The log that I found at Babcock, or that Homo erectus found 1 million years ago, that biomass is tremendously useful for energy, and we can even convert it into biofuels. So I'm going to pause for a moment and share a video with you about biofuels in case you're not familiar. You do have to bear with me and be a little patient.
We all know that it takes a lot of fuel to keep keep our country running, right? Cars, trucks, planes, trains. What if we could develop a homegrown renewable source for those fuels? Well, good news. We already are. We can create clean, renewable transportation fuels from plants, trees, and a range of other organic materials. In other words, biomass. Okay, so biomass is organic material from forest thinnings and wastes, from crops grown to produce energy, and from other renewable energy sources like algae that can all be converted into fuels. Scientists and engineers are finding new ways to make biofuels that can take the place of conventional fuels like gasoline, diesel, and jet fuel. Here's where biofuels have a great advantage. They can be made from leftovers or waste products. For example, non-edible biomass sources like wheat straw and corn cobs are often left over from agricultural production, and some can actually be used to create fuel. And in the near future, crops can be grown specifically for energy, like fast-growing trees and grasses. Right now, biorefineries with new technologies are being built to convert biomass into fuel, power, and even bioproducts, like plastics, soaps, and cosmetics. And many biofuels can be seamlessly integrated into existing vehicles and fueling systems for diesel, gasoline, and even jet engines. So, how does it work? Essentially, biomass solids are broken down and then refined into biofuels. There are a lot of ways to do this. Enzymes can be used to break down biomass into liquid sugars. Then microbes, like yeast, ferment those sugars into renewable fuel. Extreme heat can break down biomass too. When you take oxygen out of the mix, biomass is rapidly broken down to a bio-crude oil that can be refined into biofuels. Add a little bit of oxygen to extreme heat, and biomass solids are converted to a gas, and that gas can be converted into biofuel. As technology develops, researchers at the U.S. Department of Energy and its national laboratories are working to make biofuels more efficient. Sustainable biomass resources, more effective enzymes, organisms, and catalysts all help to bring down the costs of producing biofuels. The end result is fuel you can use anywhere, or any way that you would use petroleum-based fuel. Homegrown biofuels, clean and renewable, and a big step forward for America's energy security.
And so one of the things I would talk about, well, certainly if we were in the room together, are what some of the challenges might be for wide-scale biofuels. Wide-scale biomass. One of the challenges is available cropland. Another is the water that's used. And so when we talk about the food, energy, water problem that I mentioned before, often called the food, energy, water nexus, well, if you're using your good croplands that you need to grow food on for producing biofuels, well, then you have a competition between food and fuel. And same thing with water. And so what we're working on today, we being the Department of Energy and researchers around the globe, are to how to do it much more efficiently in converting what nature has come up with, photosynthesis, to convert light and oxygen into and carbon dioxide into biomass. But there is a challenge of scale. And so we're trying to overcome that. And when we think about, and I'll get to fossil fuels in a little bit, fossil fuels are in fact biofuels, biomass that was just pressurized under the earth for millions of years and concentrated into a really concentrated energy source. And so that's why it's been so useful for the last couple hundred years. When we think about what's down deep in the earth, there's another option for producing energy, and it's called geothermal. And another option is the water that's on the surface of the earth in hydropower. As the water flows from a high location to a low location and it's flowing down rivers or waterfalls, there's a lot of power that can be harnessed from hydropower. But we've known how to do that for a long, long time. And so we have dams and hydropower stations across the globe that are almost maxed out because of the amount of time that we've known how to produce hydropower. And so one of the challenges also with hydropower is the land usage. In fact, it removes it and stagnates the water into behind the dam, and there are ecological issues around that as well. So there is no free game. Geothermal deep in the earth is really expensive to drill wells. It's really expensive to provide all the material, but once you have a geothermal system, it's producing heat from under the earth, that like we do through our natural gas and our coal plants today. And so geothermal is another viable option, but it's really expensive and it's really deep in the earth unless you live in Iceland or on top of a volcano. And so in the interest of time, I did have a video on geothermal, but I'm going to skip that just for the time being. And it's not because I'm not interested in geothermal. As a matter of fact, I spent about 20 years working on developing technologies in geothermal. I had my own research when I was at West Virginia University and at MIT. There are other energy resources that we know of. Certainly wind and solar don't emit CO2 when they're producing energy. Now, certainly if you consider the full life cycle of creating the materials that go into wind and solar, there is some emissions that occur, but overall the life cycle of wind and solar do not emit CO2. So when we think about, well, what are the challenges and the benefits of wind and solar? Certainly they can be low cost. You build a wind turbine, the wind blows, you produce electricity. You build a solar photovoltaic system, the sun shines on it, it produces electricity. They can be very cost effective, but what happens when the sun goes down at night and the wind stops? Yet we still need the energy to be usable at that moment when the sun's not shining. So some of the challenges that we're facing of increased wind and solar penetration into our energy resources is how we can store the electricity that's produced when the sun is shining and then used at night. And so in fact, right now we're seeing some challenges in this exact at this exact interface of deployment of wind and solar in California and ensuring that the energy is there during a massive heat wave this past summer where folks needed their air conditioners and their refrigerators to run, but they didn't quite have enough power. And so we're trying to tackle some of these challenges. Another source of energy is nuclear. I mentioned every atom has and stored inside of it lots and lots of energy that are within the intra-atomic bonds that are holding the electrons and the neutrons and the protons together, particularly the neutrons and protons within the nucleus. And so when we think of nuclear energy, most often the type of nuclear energy we're thinking about is something called fission. And fission is when you take a really heavy atom that has lots and lots of protons and neutrons contained in the nucleus, one like uranium, and we take that nucleus and we split the nucleus in half, or not necessarily in half, but we break some of the neutrons and protons out of the nucleus to create a new molecule or a new atom. And when we do that, it releases vast amounts of energy, and it does not emit carbon dioxide. What you're looking at here at a nuclear plant, the big stacks on the left and right of the picture, those are cooling towers. You're actually seeing clouds being formed by just water from these cooling towers. And so nuclear is very clean, at least in its production. And then when you have to consider the waste that nuclear produces, it produces radioactive waste that then either has to be somehow reused or stored safely in perpetuity. And so again, nothing is free, and also nuclear is at the moment pretty expensive in terms of producing power. But some of the research going on in the Department of Energy is how we can shrink a nuclear reactor and make something called a small modular reactor that can be almost factory built, but at a much smaller scale and produce much less waste. And so there's a tremendous opportunity in the advancement of nuclear. Well, but what are fossil fuels? So fossil fuels, they are in fact fossils of organic matter that formed from decaying plants and animals from a long time ago, millions of years ago. And the most popular fossil fuels are oil, coal, and natural gas. So we use oil to create gasoline for vehicles. We use coal for heating, certainly over a century of heating in homes, but now mostly in the production of electricity at coal-burning power plants. And natural gas is also commonly used to produce electricity. So we think of the ratio of the electricity that we make in the United States, just over 30% is produced from natural gas, just about 30% or maybe a little less is produced from coal. So that's 60% of our electricity today is produced from coal and natural gas. And so one of the challenges, obviously, is the environmental impact and carbon dioxide. But when we think of coal, the United States has more coal than any other country. There are 5 states that produce 70% of the nation's coal. Those are Wyoming, Kentucky, West Virginia, Illinois, and Pennsylvania. That's 70% of the United States coal, and Wyoming alone produced 40%. West Virginia is second at about 11% of the coal used in the United States today. And as I mentioned, right around 30% of our electricity is produced from coal. But there are some other things we can make from it because, well, in fact, it is a product of decaying organic material from millions of years ago. And so we can start to break apart the chemical compounds that are in coal and produce really, really valuable materials. Certainly at even low volumes, so we're not talking about CO2 emissions now, we're looking at what can coal be used for. And so these are some research areas that we're performing in our laboratories at NETL and with our other laboratory, sister laboratories around the DOE complex. And these valuable resources can be everything from what are called rare earth elements that aren't actually rare. They're just at very low concentrations in the Earth's crust. But these elements are like yttrium and scandium are used in high technology products like our GPS systems that are built into our smartphones, even the LED screens on our smartphones and our TVs include lots of these rare earth elements. They're also used to produce the magnets that are used in electric engines, say for electric vehicles, or even in the generators that are used to produce power from wind. They all use rare earth elements, so we can find that in coal. We can also make things like graphene, which is just this miracle compound with all kinds of really cool electrical properties, and might be a building block for a range of commercial products. And then finally, another product that can come from coal is carbon fibers, and it's not just for our bicycles and our golf clubs, but when we think about what we can use carbon fibers for to lower the weight of vehicles in the future, to lower the emissions of cars on the road, it is a strong, very strong material, stronger than steel, but yet a lot lighter. And so there are some tremendous opportunities for using coal for valuable materials and not just electricity. And so those are some things that you might not know about coal. And so now let's dig in, sorry for the pun, but dig in a little bit into oil and gas and how we use oil and gas.
Every day, natural gas improves our lives. Even before this, or this. For many of us, it starts here, from the moment we wake up. In addition to being the primary heating fuel for half of U.S. households, the largest use of natural gas is for electric power. It fuels a majority of our electric grid and is depended on by important resources like hospitals, military bases, and schools. What makes natural gas such an important energy source? Natural gas is a fossil fuel found deep beneath the Earth's surface. And we're finding more and more of it throughout the U.S. In fact, new discoveries and extraction methods have led to a dramatic rise in natural gas development, making America the world's leading natural gas producer. The availability of natural gas makes it extremely affordable. And unlike other energy sources, natural gas can be stored and saved for long periods, making it a reliable energy source in times of increased demand and as a backup to intermittent energy sources. Available, affordable, reliable. That's
So we do a lot of work in how we can produce natural gas. And then finally, one of the big technology areas that we work on at NETL at our 3 laboratory locations, then we have field offices in Texas and Alaska, is how then can we develop materials that can capture the CO2 that's emitted when we burn a fossil fuel and capture that CO2 and then sequester it so it doesn't end up in the atmosphere. And so we have a whole suite of projects, 30-some projects, understanding what happens underground, not only when we produce oil and gas, but when we put CO2 back into the ground where it came from when it was coal, oil, or natural gas. And so that's what NETL worked on. And we have the research that's going on in Morgantown, Pittsburgh, and Albany. We are home in Morgantown to the 10th fastest supercomputer in the Department of Energy, which is saying a lot because three of the 5 fastest supercomputers in the world are DOE supercomputers. And so we have certainly the fastest computer in West Virginia and the region in Morgantown, which is our Joule supercomputer. And in Pittsburgh, we're doing everything from making the carbon materials I was talking about for LED displays to designing drone systems to be able to detect emission sites from oil and gas. And then in Albany, we're developing materials and alloys, including one that is a biodegradable, biocompatible material for a heart stent, which has patents around the world and is the material used in most heart stents today. And so some of our areas I mentioned, understanding what happens if we put CO2 underground and when we produce oil, coal, or natural gas. One area is in geological and environmental sciences. And so I want to share with you, and I know we're running a tad short on time, but I want to share with you the story of one of our researchers because I wanted to about careers in energy, and I think that you're going to be the future of our energy innovation. To meet Circe Verba is one of our research geologists at our Albany, Oregon site, and she has just an amazing story that touches on planetary science as well as energy science.
I have a lot of rocks at home. You know, someone might carry a box and they'll be like, "What is that, full of rocks?" If you ask a geologist, the answer is probably yes. My name is Circe Verba, and I'm a research geologist at NETL. So I grew up in rural Eastern Oregon in a small town called Pendleton. My mom really pushed art on me, actually. My sister was kind of the one that was deemed to be more likely to become a scientist. And I remember my mom got her a rock tumbler. And I was so upset because I always wanted to play with it. And when I was 14 in middle school, I took an earth science class. And that was the year where science really clicked for me. And I was like, I want to be an astrophysicist. And so I ended up going to OSU, and I enrolled in the physics program there. And so at that point, I decided that I was going to change to earth science. And it was great because it allowed me to not only encompass the astronomy courses that I had, but I got to take geology, oceanography, and atmospheric sciences. But that was kind of like the start right there. It really solidified that, yeah, I want to study Mars. So I actually have a couple things on Mars named after me. I have a pit crater, and then I have a rock from one of the Martian rovers. My path is very unique because I have the roots in planetary geology, and now I do geochemistry. My primary job is looking at rocks and trying to understand the connection from the lab to the microscope. And that's kind of my passion, is to be able to take something and look anywhere from the microscale to nanoscale. And it's really fun because then we can create these 3D images. So what does it actually look like on the surface of these tiny features to what is the elemental composition? We want to understand what phases these rare earth elements exist. And so why that's important for everybody is because everybody has a smartphone or a computer. And this technology is made out of rare earth elements. And right now we don't have a viable domestic source in the United States that we can actually extract it from. So little did my mom know, when she used to go around to yard sales and collect Lego bricks, it actually really helps with engineering skills. And so my little Lego figurine, she kind of has become my little travel buddy, like a traveling gnome. So we take pictures together when I travel to various places. To me, what's really cool about being a scientist is trying to understand the unknown. Whether you do it at large scale, like you're looking at the surface of a planet, down to something that is so tiny that the human eye can't see. It's this small imaginary world. And so that passion is kind of what drives me to understand on multiple levels, be it micro or macro.
So I know we're up against the end of time. I want to have a bit of a frank discussion, just very quickly, about our energy system as a whole. You know, every form of energy that whether it's wind, solar, biomass, hydrothermal, geothermal, or coal, oil, or natural gas, they all have some inherent challenge in implementing it at a wide scale, be it CO2 emissions from fossil fuels that we're trying to figure out how to capture that CO2 and keep it from being emitted, or it's the fact that the wind doesn't blow all the time and the sun doesn't shine, yet we use energy every minute of every day. And so we have lots of challenges in front of us and lots of exciting projects for future scientists and engineers like I hope are watching today. And so I hope to excite you about a career in energy because in fact, there is so much exciting to work on and for us to tackle into the future. So thanks for indulging me today, and I hope maybe we can have a little conversation too. Emily, back to you.
Absolutely. We have a question from Emily that asks, do you enjoy studying energy, and could you explain how your job works? So thank you for that question, fellow Emily.
Emily, thank you so much. I love studying energy because I think, it honestly impacts every single person. And one of the things we try to, we are very proud at NETL is about our impact on people's daily lives. What we do matters, and that's why I get so excited. Now, my life as a director, well, I used to do science a lot. Now as a director, I do a lot of management of science, but I get to be, and this is my favorite part of the job, I get to be the spokesperson for 1,800 employees of the National Energy Technology Laboratory, including Don Ferguson, who just joined us on the camera. I get to be the spokesperson and get to be the person so excited about the work that they're doing every single day to make our lives better. You're muted, Emma.
Thank you. I see we have a question from Annabelle, but Annabelle, your question didn't come through. So if you're still watching, go ahead and give us your question again so we can get that asked maybe later in the program. Another question, how do you handle these trade-offs? I mean, you talked about how all of these different types of energy have their benefits, but also their downsides. And so what's the decision-making process like in that?
That is an astounding question. That truthfully, that is a question that we have. So I've been working with the other 16 national laboratories. We are putting all of our scientists around the entire complex together to try to answer that question because we don't have the best answer yet. So if we were truly able to understand what's called the externality costs, the cost of every molecule of CO2 that we put in the air and the cost to society, and we could put a charge on emitting a CO2. And if we could put a charge on emitting CO2, then maybe we could reduce all of those costs and benefits to some monetary value and create a market to do it. But we can't do that today. So we have to make decisions about what we value. We have to make decisions about whether, in some instances, well, at one point in time in California earlier this summer, the question had to be answered, do we value having the lights on and the air conditioners running in the hottest temperature since 1996, or do we shut the power down? And that choice was brought on because we made a choice to install more renewables through policies that prescribed how much solar and wind were on there. And so when we think about the value, it has to come down to this trade-off of potential impacts to the environment and real and measurable impacts to the environment, and the convenience of our daily life of having the lights on anytime we flip the switch. And so what we're trying to do as scientists and engineers at the National Energy Technology Laboratory is make that choice a lot easier by innovating new solutions to those problems so for us to make fossil fuels cleaner and more reliable and more efficient, so they emit less. And if they emit less, then we don't have to have that as much of a trade-off. And then we're also at NETL working on technologies for energy storage. How can we store an electron? So when a solar panel makes an electron in the middle of the day, how we can store that to use it at night. We're working on those technologies as well. And so I have the absolute faith in the scientific community to be able to provide innovative scientific and technological advances that remove the trade-offs to make our energy just clean, reliable, and efficient through the best available technology. Sorry for a long-winded answer, but I get excited about this stuff.
That's fantastic. And yeah, that capacity for storage is really something that seems like it has to improve.
It does.
So I have a question for you. Is there one project you could talk about that you're really excited about now? And what do you think the projects that our students who are watching right now, who are middle schoolers, will be working on when they enter the workforce?
Yeah. So I'm going to give there are so many, and it's like picking your favorite child. And so one project I mentioned that I would really like to highlight because it's so exciting. I mentioned graphene as a material, a miracle material that can actually, when we look at energy storage, graphene could be a breakthrough material in the ability to store electrons on the grid. One of the limitations about graphene so far is the cost to produce it. We usually produce it either through natural gas sources or through graphite. The graphite that you have in your pencil can be used as a precursor for graphene. Well, our researchers just this week or last week, either this week or last week, were awarded something called the R&D 100 Award. It's an Oscar for innovation. They were awarded an Oscar for innovation for a new process to take coal and turn it into low-cost graphene. So much low cost that I have a liter bottle of graphene in the laboratory in Pittsburgh. That street value of that graphene is about $20,000 for this 1 liter bottle. We can make it for less than a cent of coal. Less than 1 cent worth of coal in a few hours in the laboratory, we can make a $20,000 bottle of graphene. The reason that's so exciting is then we've now produced a low-cost way of making a miracle material that might have breakthrough technologies that truly change the way we produce, store, and distribute energy and electricity around the globe. That's one that I'm a little excited about. But the one Don is working on is another one. So Don Ferguson, who will join us here in just a moment, Don is working on a project called a rotating detonation engine. And this rotating detonation engine is one in which it completely changes the way that we would use natural gas or hydrogen in a combustion engine to run a turbine. That there's interest from the Air Force. NASA is really interested in how we can do this. And in Morgantown, in the laboratory that Don's working on, we have the best rotating detonation engine rig in the world. And I say that unequivocally because we can run it for longer because we have a cooling system around it. It is the most advanced rotating detonation engine in the world. And Don is working on that here, who will join us in a second.
That's fantastic. Thank you so much for your time today, Dr. Anderson. And we are so lucky to have you here to talk to us.
Oh, it's been absolutely my pleasure. I can't wait to do it again. Emily, thank you very much.
Welcome. Our next presenter is Don Ferguson. He also works at NETL, and he is going to talk to us about the hot and cold cans activity.
Yeah, hey, thanks, Emily. So my name's Don Ferguson. I'm Dr. Don Ferguson. I'm a research scientist for the Department of Energy at the National Energy Technology Laboratory. And, doing some weird things there. And for you guys that were on during Dr. Anderson's talk, we work together at the National Energy Technology Laboratory. Just want to make sure, is your screen flickering?
Yeah, it looks weird for us too. I'm not sure what's going on.
Yeah, I'm not sure what's going on there. Let's see if we can clean that up a little bit. All right, let's try that again. How about that? Is that better?
Looks much better.
Oh, great. That was kind of weird. That wasn't really me that was doing that. That was somewhere in the cyber world, I'm sure. So anyway, so I work with Dr. Anderson. He's the lab director. I'm one of the research scientists there. And as he mentioned, for those of you that were on, my work deals with detonation. So it sounds like I'm blowing things up, but I'm not really. We're really burning things in a different way than you would through conventional means. So if you think about the fire on your stovetop or the fire that happens inside your car, those go through a process of combustion called deflagration. The concept that I'm working on called detonation is another way of burning things that helps us release more energy than we could otherwise, and then we can capture that energy and transfer that energy into a process that allows us to make electricity. And overall, that allows us to make electricity less expensive and cleaner for the environment. The technology in particular that I'm working on, called a rotating detonation engine, it uses, right now we're using hydrogen as the fuel, and we can get that hydrogen from various different processes, from, say, refining natural gas or refining coal, to renewable sources such as from water and so forth. So there's lots of different ways that we can get to that hydrogen that we can then use to power the systems that we use today for generating electricity. But I'm not going to today. I'm not going to talk so much about my particular project. I'm going to talk a little about a very specific part of my project, and that is heat transfer. And this is something that we deal with every day. Every day we are trying to move energy from one location to another, and oftentimes that energy that we're trying to move around is heat. We do this on the stovetop, we do this when we're trying to warm ourselves, and so forth. So you can see me kind of dressed in my my parka today, and it's not nearly this cold that I would actually need a parka like this. But the idea here is that we oftentimes will use materials like these to help us insulate ourselves to prevent heat transfer from happening, or to at least slow it down. We can't prevent it, but we can at least slow it down. And we do that because we want to keep warm. So I'm getting really warm, so I'm going to take this off and talk a little bit more about the activity that we forwarded in. So, all right. So now I'm much more comfortable. So the activity that we sent in was called hot cans, cold cans. And the idea here is to better understand heat transfer. So heat transfer happens through three different basic processes that we often think about for heat transfer. There's conduction, convection, and radiation. And we see these all three, every day in our lives. And these three means of heat transfer are important for just about everything we do. Again, from driving our car to cooking to the weather, heat transfer is involved in that. So in the activity that we sent, the idea was to take a couple of different aluminum cans, Coke cans, water cans that I have, or the like, fill those with a certain amount of water at all at the same temperature, and then insulate each can in different ways, either with no insulation, which would be our control, to different types of insulation, and then observe the effect that has over time with regard to how the heat is lost from the can to the environment. And I guess that brings up a good point. When we talk about heat transfer, we're always talking about moving energy from something that's hot to something that's cold. We can't really move energy in the other direction. We can't move from cold to hot. We're always moving from hot to cold. And understanding that helps us do things like designing better insulation or designing ways of moving the energy faster if we're trying to cool things down. So depending on what we're trying to do, either maintain a temperature, cool something down, or heat something else up, will dictate the types of systems or the types of approaches we use for transferring that heat. So before we get to the experiment, just talking a little bit more about some different examples of heat transfer. If you ever just from some very basic area where you have heat transfer, all the way back to prehistoric times, I was thinking about fire and sitting around the fire to keep ourselves warm. Right. So whenever you're sitting around a campfire, you're feeling that heat coming off of the fire there, even though that you're not touching it. Right. You're nowhere. You may be several feet away from the fire, but you can feel the heat coming off of that fire, and that happens through a process called radiation. Right. So radiation is transfer of heat through waves. It's how the sun's energy gets to Earth. Right, the sun is radiating out that energy, and the sun is radiating off many different types of forms of energy, and some of that energy that occurs in, say, the infrared is what our Earth absorbs as heat. Right, so we're feeling that radiated energy or that heat energy in that way. So we don't have to be in direct contact to feel that heat. The type of energy or heat energy transfer that we need to be in direct contact to be able to feel is a process called conduction. Right, so that's where we have a hot skillet on the stove and we accidentally touch that skillet. Because we're making that direct contact, there's heat transfer that occurs from that skillet to our fingers, and that's how we know that things are hot. So we see that in lots of different processes where you may have a hot surface touching a surface that you want to dissipate that heat to. For example, some of the things that we do in energy transfer is a process called energy storage. So we're trying to store up that energy to use for other times. So for example, with renewable energy, where you have sun either solar energy or wind energy, there are times when you may be producing more energy than you can use at that moment, and you'd want to save some of that. If possible, you want to save or store some of that energy to be used for later on. So one idea is to store it in batteries. Is one idea, but another idea is to store that energy in the form of thermal energy. So taking solar energy or even wind energy and generating heat from that, and then storing that in, say, a large slab of concrete, or in a large mass of sand or something like that, where you can save up that energy, or in molten metals, where you may save that energy for use at a later time and then extract that energy later on. So that, a lot of that storing of that thermal energy happens through a process called conduction. And that's, again, where there's direct contact between objects to store that energy. And then finally, the last process is convection. And that's where you're transferring that heat by moving a fluid across another fluid. And we often think of moving air across an object. So when we stand out in the wind, you might notice that you feel colder even if the air temperature is the same as at times when there isn't wind. So just because the air is moving past you, it is removing heat from you, or the energy from your body. The heat energy from your body is being transferred to the air, and then is kind of being blown away to where it may go and heat something else. So you see this in processes like a car radiator. So if you ever opened up the front of your car, in there you would see a radiator, and there's lots of different means of heat transfer going on inside your car, but one is air flowing through that radiator, and as the air flows through the radiator, it's removing some of the heat that's occurring, or that's collected in that radiator. So you have water flow all throughout your engine, water and some other fluids that are flowing all throughout your engine, and it's through conduction that it's picking up heat energy all throughout your car engine, and that fluid then gets transferred into the radiator, where then it has air passing through that radiator. The air is not in direct contact with the fluid, but the fluid is in contact with metal of the radiator, and then the air is in contact with that metal, and it transfers the heat from that metal to the air that's passing through there, and carries it off, so that your car doesn't overheat, doesn't get too hot. Another example of energy transfer through convection and conduction, and even radiation, is the inside of a computer. So here I have the inside of a laptop computer, and there are extensive means of transferring the heat that's generated inside this computer to get rid of it. Heat will slow down the processes that are occurring in the computer. It slows down the memory, the materials in here, the memory and the hard drives and everything like that. The performance of these is less than they are when they're cool. So computer manufacturers go to great lengths to try to cool down computers in order to make them work more efficiently. So in here there are these heat tubes, and I know you can't see this all that well, but these tubes that are in here help transfer the heat from inside the computer, and then there are these fans that blow. So they're pulling in air, pushing it past these heat tubes, and then blowing that air out. So there's a combination of conduction and convection that's occurring in here. Other examples inside of here are these little pads that you see here, and they're coated with a material that will help transfer the heat quicker. And you can't see it, but on the bottom of this little plate here is another material similar to this, where it's made of a material that helps to transfer the heat quicker. So again, when we think about designing components like computers and other things, and we think about how the heat is managed in those, there are times when we want to quickly cool things down, and other times when we want to keep them warm. And in this case, we want to try and get rid of the heat as much as we can. So we find materials such as these that help dissipate or get rid of the heat as quickly as possible. So those are some examples inside of a computer, and there are lots of different examples all around the place. So let's talk a little bit about this looking at the experiment that we had sent in as our activity. And before we actually look at the experiment, I'm going to go ahead and share my screen here. And I think I am. Give me 1 second. And pull this up. All right, so hopefully you guys can now see my screen. Let me get to the up one. We'll get to that picture in a minute. But first I want to talk about how we design experiments. So when we do an experiment like this one, we're doing this experiment to figure something out, basically, to understand processes better, or to design something that we might use in everyday life. So as we do this, we go through a process, and we call that process the engineering design process. And we do this sometimes, as an engineer, sometimes we do this without thinking, and even without being an engineer, sometimes you go through this process even without thinking. But when we do an experiment like this, we want to sort of formalize or really think about each of the different steps of this process. And that helps us, one, design a better experiment that will then, two, ultimately lead to the answer that we're trying to get, right? So we begin this process by asking a question, and in this case, our question is, how does heat transfer vary from one material to another, right? So we want to look at how can we accelerate heat transfer, or how can we slow it down? That's the kind of the question that we're asking. So as we ask that question, we're going to use some critical thinking and some critical thinking, and to help us identify the need, what we call the needs and constraints of our problem. In this case, we're talking about transferring heat from a soda can. So we have some constraints in terms of the size, the shape, and things like that of the can. So, and then we're gonna research this problem a little bit. We're gonna maybe see if there's an existing solution, or are there things out there that help slow down or speed up the transfer of heat from Coke cans or soda cans. So we'll look at whether past solutions, or maybe just kind of look at heat transfer, try to understand heat transfer, the concept of heat transfer a little bit more. So we'll just kind of do some research there, do some reading, and maybe conduct some simpler experiments to help that would lead to this bigger one. And then we're going to kind of brainstorm or imagine some possibilities here. In our case, we're going to think about what types of insulating or conductive materials or materials that will help transfer heat quicker, so we'll accelerate that process. So we're going to brainstorm and do some creative thinking about the types of materials that we may use. Then we'll develop a plan how we're going to conduct our experiment. And sometimes, in this case, we're doing a physical experiment, but sometimes we might do a computer experiment. We can do this same experiment in using computer models, where we generate a model of the can. We understand, lots of people have made measurements like this before. So because of the measurements that have been made, we can take some of the basic principles and the basic properties of things like aluminum and water and things of that sort, and develop a computer model that will replicate our physical model. And that's something that we do a lot at NETL is, we have a physical experiment, but then we also have computer models that run along with those. And Dr. Anderson before me had talked about the supercomputer that we have there at NETL, and oftentimes we'll develop models that will run on those supercomputers. And some of these models, for this type of experiment would be a model I could run easily probably on my laptop computer. But when we start simulating bigger things, we need to use these supercomputers that have thousands, tens of thousands of processors on them, and all those processors work together to split the problem up to make it to be able to solve these big problems in a short amount of time. And I will say that supercomputer itself, one of the big concerns of that is to manage all the heat that comes off of the computers that are inside there. So that the building that houses that computer was specially designed to help mitigate or get rid of all the heat that's generated from those computers. So we develop in the plan. It could be a physical experiment or a computer model, and then we'll run the tests. We'll run these tests, and we run the tests, maybe multiple times to make sure that we have repeatable data. We think about how we have how we have control processes, and then we have our dependent variables and our independent variables and things of that sort when we run our experiment. And one of the things that I note here on this slide is that it's okay to fail. It's okay if our experiments don't work out the way we originally planned. When we think about experiment, one of the things that we want to do first is make sure that we're conducting our experiment safe, right? So we're always taking precautions to do it safely. Experiment like this is a pretty safe experiment. So that's taken care of. But it's okay that if our experiment fails and we don't, if we had different materials that we're looking at to check to see if they insulate or conduct better, it's okay if they all had the same result, right? Because we're going to learn something from that. So that'll help us design the next experiment a little bit better. So don't worry about failure. Failure is, a good thing in that we do some creative thinking to try to come up with a solution, and then we try it, and then if it doesn't work out, then we learn from it, right? We learn from it, and then we make some improvements to the next experiment, so that when we run the experiment again, we do get to a point where we are able to answer the questions that we want a little bit better. Okay, so I'm going to stop sharing my screen for a minute and get back to my camera and take a look at our experiment that we have over here. So back behind me, I have my experiment, and I have it set up maybe a little bit more elaborate than what you might have if you do this experiment at home or even at your school. So what the experiment asked you to do was take a couple different cans, a couple different soda cans, and figure out a couple of different types of insulating materials that you might consider that could either accelerate heat transfer, speed it up, or slow it down. So I have a couple different things set up here, and we're going to look at some of the results they have here. So first, what I have, and I'll talk through my different setups. So I have, in the handout that we provided, they had mentioned using thermometers, right? So instead of thermometers, I'm using a device called a thermocouple, and these measure temperature just like a thermometer does, except I can now record all that stuff on the computer, and then we can look at what's going on there. So I have a thermometer over here, a thermocouple, and you can't see it very well, but it is, let's move the camera in a little closer, so maybe you can.
All right, folks, it looks like we're having some technical difficulties with our connection to Dawn through Zoom, so we'll be back in just a couple of moments once we get that sorted out. Thanks for your patience.
Did his internet Hello, everyone. As we are waiting to just wrap things up, we're going to play a Kahoot for a bit. This is a general day in the park energy Kahoot with only 6 questions. This will be very short and sweet, but it'll be as fun as all the other Kahoots that we've done. So, on any browser, on any device, maybe name it iPad, iPhone, tablet, Android, computer.
Okay, I'm back.
Just enter kahoot.it in the browser with this game pin, I74387. Okay, so I was just informed that we will be only doing about 3 to 4 questions for this Kahoot to make it short and sweet, even shorter than just the 6-question one, but again, it'll be just as fun. I'll cap it at 4 questions and I'll give you guys about 2 minutes to join, or about a minute to join. I'll give you guys about 20 more seconds. And we're gonna start in 3, 2, 1. How much power does your phone chargers use if you leave it unplugged in when you are not charging your phone? (0.1 to 0.5 watts, 2 to 5 watts, none, about 1 watt. I'm very guilty of leaving my phone charger in, so please do not come for me. 0.1 to 0.5 watts may not sound like a lot, but it adds up over time. Snowy Frog in the lead with 781 points. Which area is predicted to have the most new jobs created over the next 10 years? Nurse practitioner, electrical engineer, solar panel installer, or teacher? Solar panel installer. Jolly Chicken now joining Snowy Frog on the board. Which of these words describes energy produced by using heat from inside the earth? One of our presenters just went over this. Is it solar, wind, exo-botanical, or geothermal? I'll give you guys a very short hint. Use suffixes and prefixes to your advantage here. geothermal. Geo meaning earth and thermal meaning heat. Snowy Frog on fire with Fast Bobcat joining the leaderboard. We're going to move on to our last question here. Which of the following is an example of renewable energy? Electricity from a wind turbine, electricity from a coal-fired plant, gas for your car, or just any type of electricity, any type. Electricity from wind turbine, that is correct. We are going to look at the leaderboard and we're going to call it a day for this session. Snowy Frog in first place with 3,044 points, followed by Jolly Chicken, Fast Bobcat, Tropical Lion, and Dr. Impala. Sadly, Dr. Impala did not get any points, but that will be all for this session. So we're going to head right back to the session where we were cut off. I hope to see you guys soon.
All right, so sorry about technical difficulties, but I'm back, and I was explaining the experiment that we have here. So first, I have a thermocouple on the far end over here, and that's just measuring the ambient temperature. So that's one of the ways that we look at the control. We want an idea of what's the temperature of the water that we put inside the can, and we just heated up some water in a microwave and then poured it in the can. Of course, we didn't put the cans in the microwave. So we have just a thermocouple to measure the ambient temperature. And then our next one is our basic can without any insulation at all. So it's just the can itself with the water that we poured in there. And ideally, what I did is I put a container in the microwave, heated the water up for about 2 minutes, and then poured that water carefully into the can. That water is going to be warm or hot, depending on how much water you had in there at the time when you heated it up. So you want to be careful when you're pouring the water into the can. All right, then my next one, I have cardboard wrapped around the can. And then the third can I have here has got a Huggy, what are called a Huggy, and it's a big styrofoam insulating material that's made for cans. To keep the cans either warm or cold, depending on what you have in there. So it's intended to limit the amount of heat transfer that occurs in the can. And then I have a pot here that's got water in it. So this is water that I've allowed, that I let sit out here for a long time to get to the same, to get to about the same as ambient temperature, to see how quickly we can dissipate the heat from the can into this water. And also through conduction, because the water's touching that can and so forth. And then if we go a little bit further, I have a sort of a secondary experiment going on here where I'm looking at convection. So I have a fan, and then I have another sort of baseline thermocouple here that's measuring the ambient temperature from the wind that's being blown out of the fan. I have a control can here to get the effect of convection without any insulating material, and then I have just the Huggy that's back on here. So this is how we design an experiment. These cans have been sitting out here for a little while now, and I've been collecting the information, or collecting the data that's run off these cans, so we can take a look at that data and talk through that a little bit. So I'm going to share my screen again, and here, so the intent when you guys run this experiment is that you're going to you're going to collect every 5 minutes. You're going to take the temperature. So you have your thermometer that you can stick down each of these cans. You need to collect the temperature every 5 minutes. The beauty of the nicety of the thermocouples here is I can have them connected to the computer, and then it can just continuously record the temperature over time. And you can do this. I have maybe a somewhat elaborate system here, but you could do the same thing with, say, a Raspberry Pi or an Arduino or something like that if you wanted to record all this stuff in the computer. So what you're seeing here on my screen is graphs that you would be creating if you were once you collected the data and then you recorded the data onto a graph. And oftentimes we'll use graphs like this to help us visualize the information that's coming. So if we look at so this first chart that I have up here that you're looking at is the results from our conduction experiment. So that was the experiment that we had that I talked to first. And the dark blue line that you see here on the bottom is our ambient temperature. So this is if we maintain that temperature over time, eventually all these cans, the temperatures from all these cans would reach these levels. Is what you would eventually see. All right, and then the next one here, and these are actually mislabeled some amount, where the green line that you see here is actually our I'm sorry, this green line. No, take that back. This dark green line, or the bright green line that you see here, is our baseline can. So that's the can without any insulation on it at all. That's just the can out there by itself. And you can see that it's cooled down a little quicker than the other cans with the insulation. So again, these are mislabeled on my legend over here, but the two cases that you see here, the red case is the cardboard insulation, and the blue case is the Huggy. And you can see that in this case there wasn't a big difference between the cardboard and the Huggy. So the cardboard is a pretty good insulator compared to the Huggy, at least for this short term, and for the difference between our ambient temperature and the initial temperature of the water, which is a little bit off the screen now because I've been letting this run for some time. So these top four lines would have all started at the same temperature, and then over time you'd see them drop. And then finally, this line that you see here is from the case where we had the can submerged in the water. And you can see that by submerging that can in the water, we were able to conduct the heat away a lot quicker. So the water is absorbing a lot more energy than what we would be losing in the other two cases. And if I jump to these slides real quick, this slide shows an example. So I took a picture of the cameras with I took a picture of the cans with an infrared camera, and the infrared camera is a way of looking at the amount of heat that is being given off, and this is not really a calibrated image. So we're just kind of getting a general sense of what's going on with the color, but you can see that all four of these cans in this case are brighter than the surrounding area, which means that they're giving off more heat than the surrounding area. Now this, the one with the water in here is a little misleading because water absorbs infrared energy. So this picture is a little bit misleading, but you can get a sense at least in what's going on with the heat transfer from the other cans here. So let me jump back to my graphs and I'll switch over to the conduction convection case. And in this case, we see our ambient temperature, which is this red one, and then our baseline can, which is this green one, and then the Huggy, which is the dark blue. And if we look at these temperatures, and this experiment's been running the same amount of time for each one, And if we look at our baseline can, which is now around 20, out here we're about 23 degrees Celsius, comparing that to our baseline can over here, which is still at around 33 degrees Celsius, we can see that convection helps to move or transfer that heat a lot quicker than we can with just conduction by itself in this case. So we really use the conduction, or that wind, that air moving across the can, to help transfer the heat a whole lot faster. So that's the experiment, and then the idea then was that once you guys run the experiment, that you talk about the results and maybe think about how you might redesign this experiment to maybe look at other insulating materials or other ways of either insulating or conducting the temperatures. Maybe make some changes with the fluid that's inside. Instead of using water, maybe you could use Jello or something else, and just kind of get a sense of how making changes to this might change how the heat is transferred. So with that, I got a few minutes, I guess a little bit of time left to answer some questions. If you guys have any questions about either the experiment that we did, the activity that we did, or about the work that I'm doing at NETL, or anything else that might be related to energy or engineering.
We do have some questions. Ryan asks, I noticed that your experiment is running on LabVIEW. Is that a skill that would be useful for people to have, or that you usually use at NETL?
Yeah, so LabVIEW is one of the programs that we use for our data acquisition at NETL, and it's often, and there are other softwares out there as well, but it's certainly one that we use quite a bit at NETL. And it allows us to do a lot of, we have a lot of control over the experiment. We can really design how we save the data and then analyze the data in LabVIEW. But certainly having those kind of skills to be able to take information from a sensor, in this case a thermocouple, and collect that information is really important for not only science but everyday life. If you think about our cell phones, right? Our cell phones are packed full of sensors. From just, you saw me just kind of shake the phone and it turned on, right? So there's a little gyroscope in here, or inertial sensor, that measures the movement of this phone. And all that information is, and let me back up, and we're seeing the use of sensors more and more in our everyday life. We have sensors that turn on the lights as we walk by, or sensors that count the number of cars that drive through a certain area, or sensors that keep count of the number of people in a building to make sure that you don't have too many people in that building, especially when you're trying to keep social distance and things of that sort. So we're seeing more and more use of sensors, which are then collecting data, which then needs to be analyzed. So from collecting that data using data acquisition systems like the LabVIEW, to analyzing that data using software programming languages like C and Python and Java and things of that sort, to where and then other programs, software programs like MATLAB and Octave, and those are all ways of collecting data and then analyzing data, which are critically important skills for not only a scientist but now almost everyday life.
Absolutely. Dr. Ferguson, thank you so much excuse me, for being with us today and sharing this really neat experiment.
Yeah, my pleasure. It was a lot of fun. And if you guys have any questions about NETL, you can always look me up there, or energy, or whatever follow-on questions you might have. I'm always around.
Our next presenter is Wayne Yonkelowitz. He has worked with the National Energy Education Development, or NEED program, for many years, and he is going to share a really cool activity with us. It's on the website if you want to do it yourself, called Candy Collector.
Hi, everybody. My name is Wayne Yonkelowitz. I live in Fayetteville, West Virginia. I am a retired 8th grade science teacher, taught for 31 years, and also taught high school astronomy and earth science. I've used NEED in my classroom since 91, and really believe in the NEED program. Also been on the teacher advisory board for many years. NEED, as Emily said, is the National Energy Education and Development Project. We're a nonprofit organization, and we have a K-12 energy curriculum, and everything at the NEED website is free and downloadable for you to use, and it's in a PDF format. And before I start the activity, I'm going to go ahead and share my screen with you and show you a little bit about the NEED program, just real quick. So this is the NEED website. It's nee.org. And we're kind of looking under the educator tab. There's a tab for students. We have our annual youth awards every year that we hold in DC. This year it was virtual, and hopefully we're back there next year. That if your kids do any type of recycling, energy conservation activities and so forth, you can read about what they need to do, and they enter at the state level, and there's a contest. We have state winners, and then we have national winners, and everybody's invited in DC to share and participate. It's at the end of June, and they get to tour DC. We have hands-on activities, we have dinner cruise, and then we have recognition. But all the information's right there under Youth Awards. For the teachers, you can see the resources we have. All our materials are coordinated to state standards. And if you go down the curriculum, you can see what's available, or you can just double click on the curriculum resources. It will take you to our planning guide if you've never used NEED. We have a step-by-step suggestion on how to use the NEED materials. We have primary guides, elementary, intermediate, and secondary. Intermediate's like middle school on there. For my classroom, which 8th graders, depending on the kids, I use the intermediate and secondary activities. Or you can go down through and look at particular subject areas: biomass, energy resources, and wind. So I'm just going to click on wind real quick. And if you go down, you'll see we have Wind for School, we have secondary energy info books. And what that does is it talks about all the energy sources. There's a difference between energy, forms of energy, and energy sources. So these books here talk about all the types of energy sources, gives background information, the good and the bad about them. And we also have kits that you can buy, or you can put your own together. As long as it says 0, then then it's not going to cost you anything. You would click on this, and what it does is it takes you through a checkout process, such as this. When you go to add it to your cart, you go through a checkout process, and you can have your kids sign up. We can add this to it. On that, it's already got where I have an updated on there. So you can go through, again, a checkout process. As long as it says 0, then basically you are, again, getting it for free. It's downloadable, again, PDF format, and you can print out as much as you want or as little as you need. And then we have other sources here, and we do cover all the sources or all the forms of the energy that's out there: natural gas, solar, the whole gamut. We have games, skits, plays, debates, anything that you might need to address your energy concerns, or again, to meet your state and federal standards on that. So enough with that there. And so what I'm going to do is go ahead and get back into, stop sharing my screen, try to, on this. And there we go. And so the activity I'm going to do is called Candy Collector on this. And as Emily said, it's on, she did share a copy of this. This particular one comes out of our energy games and icebreakers. Okay, so this activity, again, comes out of our energy games and icebreakers. So what you're going to need for your students, or if you already have, is you're going to need at least 50 M&Ms. If you're working in groups of 4, which my students did, each group will get 50 M&Ms. If you're working individually now because of COVID and stuff, then you could do down to 30 M&Ms per student. You'll need 3 bowls. You'll need, for the little kids, what we've found out is that small flat plates work a lot better than the bowls. They have trouble sometimes getting out of the bowl into another bowl. You're going to need 3 jelly beans for later on, or again, I'll talk about extensions that you can do with this. You'll need a plastic straw for each student on that, okay? So the way this activity basically works is that the M&Ms that you have in your plate or in your bowl represents an energy source. And each person or each group of students represents a town, and each town, again, has its energy source, okay, on that. And what you're going to do is you have to use your straw to remove the energy source into a blank plate. And you have 15 seconds to remove as many M&Ms as you can from your source into the empty plate. So what you're doing is, remember, is that each one of the M&Ms is an energy source. So in that year, you are using up your supply of energy. So each student then removes as many M&Ms as they can in 15 seconds for your town to use. When you're using the straw, you cannot use your hands. Basically, the way it works, and it does take a little practice, and it's funny, is the fact that you are going to put the straw in your mouth. Once the straw is in your mouth, you can't use your hands. And what you're going to do is you're going to use the straw and use it that way. So you get 15 seconds to remove as many candies as you can. At the end of the 15 years, or sorry, at the end of the 1 year, what you do, and I have this made up for my kids, is they use a chart. It's got 3 columns: the amount of energy used in that year, the amount of energy remaining, so they know how much resources they had to begin with, and the estimated number of years of energy supply. So for example, if they move 10 M&Ms in the first year, that would be the amount of energy used, 10 units, however you want to do the units. That amount of energy remaining would be 40 if they started out with 50. And then what they have to do is based on how much energy they removed that year, they want to then estimate how much energy does that town have remaining for them to use. So what you can do, or what you do then, is you now play another round. So this will be year 2, and they again remove as much energy as they can in that 15 seconds. Then they recalculate how much energy they used, how much is remaining, and how many years left does the town have for their energy supply. Then you can do a round 3, and it's the same process, okay? So then what they're doing at the end of every year, that candy that was removed goes into that 3rd place. That's waste candy. Now, don't let them eat it yet, because they're going to use it again, okay? So they put it into that waste bowl or waste plate and don't use it again. So you can do 3 or 4 rounds that way. Then what you do is you introduce 3 jelly beans into the bowl. In these rounds here, what they do is now each student in that group of 4, they're only allowed to remove 2 energy sources. Okay, that 15 seconds or 1 year, they can only remove 2. If you're doing this as an individual student, I allow them to remove 4, no more than 4 in that 1 year. And so they go ahead, and just like the last process, they have their 15 seconds to remove as much energy as they can. They're going to recalculate again how much energy was used and so forth. But here's the kicker. If they remove an M&M, if they remove a jelly bean, they can now take that jelly bean and put it back into their original source. The M&Ms that were in the bowl now go into their waste container. So the jelly beans go back into their original bowl. And you played another round. 2 or 4. If, again, they calculate, if they use the jelly bean, then the jelly bean is removed and put back into the resources. And you can play as many rounds as you can here. So my question, or what your question is going to be for the students now, is what do the M&Ms represent? What energy source or sources do the M&Ms represent? And the M&Ms represent non-renewable resources. And so you go into the discussion of what non-renewable resources are. And basically, non-renewable resources are resources that we are going to run out of in our lifetime, okay? Not that they're not being formed. They're being formed right now. Coal's being formed right now. Oil's being formed right now, okay? But it's a matter of the fact that they will not be in usable form in our lifetime. We're never going to really run out. It's just the fact that a usable amount may run out in our lifetime. The jelly beans represent what? That's going to be our renewable resources, such as wind, solar, hydropower, okay, those kind of things. And so now this is a fun way to introduce what renewable and non-renewable resources are to the students. And then once they do that, now they can eat the candies, okay? It's an edible science activity. If you have students that are allergic to the M&Ms or to chocolate, you can use Skittles. Any type of small bits of candy work that way. As an extension, again, depending on the grade level of your students, you can have them chart the graph, chart the information, or, on that. They could do it with a spreadsheet, or you could do with a regular graphing on that. You can adjust the amount of resources every town has. So some kids may have more non-renewable resources than other towns, and some towns will have more renewable resources. So there's a lot of ways that you can do that. And those extensions are suggested on the back of this activity here. So it's a fun and easy way to introduce renewable and non-renewable resources. So I use this candy collector kind of as an intro, just for my 8th graders. It's more of a fun way to review and make sure they understand the difference between non-renewable and renewable resources before we actually get into the sources of energy. So with NEED, we also have a kit where we talk about forms of energy, and it introduces the kids to the forms and introduces the transformation of energy from one form to another form. And I really use that one first to introduce my energy forms. So that is what we call Candy Collector. It's, again, a fun way to introduce the terms or renewable or non-renewable resources, or again, a good way to hold a review with the kids.
Wayne, thank you so much for sharing that activity and all of the great NEED resources with us. We have a question from Kyle, who asks, what is your favorite part about learning about energy?
My fun part is just understanding all what goes on behind the scenes. With NEED, we get into a lot of the activities, and a lot of our workshops for teachers involves tours sometimes. So I've got to actually go on oil wells and behind the scenes a whole lot with power plants and stuff. Well, it's just constantly keeping up with the new technology that's out there and the advances that we're making in the renewable energy and how we're getting better at using the non-renewable resources also.
Absolutely. So is there a favorite field trip that you've been on you could tell us a little bit about?
I think my favorite one was actually, geez, we've done quite a few. I think it was just going out. We were in Wyoming, and we went to a very large open pit coal mine out there, and just seeing the size of this equipment. I know you see it on TV and stuff, but when you're standing next to, a operating machinery, and the tires are just huge, and we got to take pictures in front of a oh gosh, I'm trying to think, a bulldozer that just picked up a bunch of coal and dumped it. And so one of the participants accidentally stepped on the bucket, and it was so hot from dumping the coal that it melted the soles of his tennis shoes.
Oh, jeez.
Okay, and you wouldn't think about that, but there was energy right there in the use. And we've been to, again, inside a hydro plant and nuclear power plant. So it's just exciting to see what's going on that.
Well, thank you so much for being here with us today, Wayne, and sharing this great activity. We really appreciate it.
Thank you for asking me to do it. And hopefully next year it's not virtual and we can do this all face to face.
Absolutely. I would love to try some of those M&Ms.
Well, you can have some. Thank you.
Welcome. I'm going to be your presenter for this next activity. And so what I want you to do is wherever you're sitting, wherever you're watching this, I want you to just touch some of the different objects that are around you and just feel what that sensation is of touching those objects. So whether it's, a pencil, a piece of paper, a table, the chair you're sitting in, just touch those different things and take a moment to just experience what that feels like. Okay, and now I just want you to rank those objects that you touched from which felt the most cold to which felt the most warm. So in my immediate surroundings, I've got a wooden windowsill, and that feels kind of warm. I've got some paper in this notebook next to me, and that's a little bit cooler than the windowsill. I have this pen that's made of plastic, and it feels cooler than the paper. And I have this just a metal water bottle, and it feels cold. When I touch it, it feels cold to me. So that's my ranking. I've got something that's wood, and then paper, and then a pen, and then my water bottle that's metal. So thinking about it, it's really obvious when we touch something, whether it feels hot or cold to us. But those objects that I just mentioned are all at the same temperature. They're all in the same room. There's not like some sort of little air conditioning unit that's inside of here. The wood doesn't have any like sort of combustion going on inside of it that's making it warmer. Those things all are the same temperature. Now, I've got a cup of ice that I'm going to use here in a minute, and that is legitimately a different temperature than these other things that are kind of at ambient room temperature. But even when we have these objects at room temperature, why do some things feel colder and some things feel hotter when we know just objectively that they're at the same temperature? And that's the question that I want you to keep in mind as I do this little demo over here. So give me a second to get set up. All right. So next to me over here, I have a wooden cutting board and just a metal sheet pan like you would use to bake cookies, okay? And I'm gonna take a couple pieces of ice here, and I'm gonna try to find ice that's about the same shape. It's gotten a little melty, but I'm gonna try to go for ones that are the same size. And I'm gonna put one on the cutting board, and I'm gonna put one on the metal sheet pan, and I want you to think about what's gonna happen to them. What can we predict will happen to these two pieces of ice? Is one going to melt sooner? Is one going to melt slower, faster? What's the difference in these conditions? And we're going to let it melt for a little bit. So send me some questions in that form. You can get to it through the website that's linked here. Or if you're on a separate device, it's at bit.ly/DIPQA. And so that's how you can submit some questions to us. So you can already see this one right here, there was a little bit of water that dripped onto the cutting board, but I'm not seeing a lot of water under that ice cube. This one that's on the metal pan is in a puddle. Like it is really melting a lot faster than the one that's on wood. So when I touch these two things, the wood feels warm compared to the pan. The pan, when I touch it, feels cold, even though I'm touching it far away from where the ice cube is. So I'm probably not experiencing how the ice cube is changing the pan. So why is the one that feels colder the one that is melting the ice cube faster? This is kind of a confusing question. Like, we experience these materials every day in our lives. We come across these things. We understand that if you're going to touch a metal pole, it's going to feel cold. But why would a cold thing melt an ice cube faster? I really wish that I could just have this conversation with you and get some of your ideas, because I'm sure you are having fantastic ideas to explain this phenomena and why my ice cube on my piece of wood is not melting while my ice cube on the metal tray is in a puddle right now. So to sort of prompt more thinking in this direction, what would happen if I put the wood and the metal tray into water? Like if I had my bathtub filled up, which I don't right now. Now I wish I had filled my bathtub this morning so I could take it in there and show this. But what do you think would happen with these two things? I'm guessing that some of you said that they would both float. And the metal is probably spread out enough. It's kind of shaped like a boat, right? Where this metal tray might float on the water, as well as this piece of wood, which would probably also float on the water. Lots of times wood has a low enough density that it might float. And the density of the metal is still going to be much denser than water, but because it's spread out so much and has sort of air taking up some of that volume, it's going to float. However, as soon as I push it under the water, if I filled the tray with water, it would stay on the bottom. It's not going to be buoyant and come back up. The piece of wood, if I push it under the water, would come back up if it was buoyant enough, if it had a low enough density. So do you think that density might have something to do with the different properties here? We can see the ice cube on the wood is starting to melt, but there's very little ice cube left on the metal. So the metal pan is a lot more dense than the wood. It has more atoms in it per amount of space that it takes up. And so those more atoms are in contact with the ice cube better. They're also in contact with your hand better. And so they're transferring more energy to you when you touch the metal, or sorry, they're pulling more energy from you when you touch the metal because there's more of them there. Okay, and so to kind of extend this, I'm going to turn my video off. I'm going to try to turn my video off. Okay, I'm going to share with you this really neat simulation that is available on a website called CK12. And if any of you educators watching haven't seen CK12, it's a fantastic free resource of science and math and other kind of curriculum. And so it starts with the question, why does the metal oven in the oven burn you, but the air doesn't? So if you've ever had that experience of baking cookies in the oven, you know that if you just stick your hand into the air in the oven just for a short time, you aren't going to burn yourself, even if the air in the oven is very hot. The air is at 350 degrees, if that's what you set your oven to, just like the metal pan and the cookies are. But if you touch the pan, you'll get a burn instantly. So how come 350 degree air won't burn you, but 350 degree metal would? Okay, so if we look at this simulation, you can see they have these little white balls representing atoms, okay? The ones on the bottom of the oven or in the pan, you can see are tight and packed together, and they're not moving very far, but the reason they're not moving very far is because they're constrained. All of their energy is just kind of vibrating back and forth, and that's how atoms in solids are arranged, okay? So I'm going to replay it a little bit, but we're going to go ahead if I can. No, I can't. You notice that the white balls that were bouncing around in the air, those were the air molecules, and they're much more spread out. Air is a lot less dense than metal is. And so even though they're at the same temperature, they're able to give you very different amounts of energy in a very short amount of time, okay? So if we look at the temperature, no matter how I change the temperature of the air, which is the blue line here, no matter how I change it, the temperature of the pan is going to be the same. If it's in an oven, it's in a closed system, and so everything in that system is going to be at the same temperature. All right, so our air and our pan have the exact same amount of temperature. They're at the same temperature. However, the thermal energy, which is on here, really changes. You can see when the thermal energy of the air, or when the temperature of the air is lower, we start out with the thermal energy in the pan being much higher. And then as we increase, this thermal energy is increasing faster. So because there are so many more molecules, so many more atoms in the metal than there are in the air, they have much more energy, even though they're at the same temperature. Okay. And so as part of CK12, there's a lot of content built around this. I'm just showing you the simulation, but there are questions that check for understanding. There's things to read about it, and various different activities that you can do alongside this if that's something that you're interested in. So now that I've shared that and a little bit of explanation, I'm going to show another experiment, if I can get my phone to work. And it's still going to involve ice because that's what we have on hand today. You'll notice that our ice cube on the wood is definitely smaller, definitely has a wet splotch starting to form around it, but our ice cube on the pan is completely gone. You can see some little air bubbles in the water, which is interesting, but we have no more ice cube. We have a puddle and we have an ice cube on the wood. I'm going to melt this one too, because I want to ask you what is going to happen in this new experiment. I have one glass that is empty, okay, and I have another glass that is full of just room temperature water, okay? So this is water that just got taken out of the tap. Oh, there, that's much better. Water that's out of the tap and has been sitting around for about an hour now. And I'm going to put an ice cube. I'm going to, again, try to make it the same size for both of them. And I'm going to put one in each. So which one do you think will melt fastest? Will it be the one that's just in room temperature air, or will it be the one that's in room temperature water? Okay, so I'm going to grab my ice now. Let's see, that's a decent sized one. Oh, that one's different. Let's see. Okay, these two are about the same size. I think this one's a little bit bigger and I'm going to put it in the water, so we'll keep track of that. And then we've got one that's a little bit smaller in the air condition. Let me get a good background on this. Okay. So I know that you probably didn't sign up for this today to watch ice melt, but that's what we're going to do for a little bit. I'm so curious to hear what your predictions are about whether you think that the water condition will melt first or whether you think the air condition will melt first. Again, the air and the water are at the same temperature, okay? We have the same amount, or we have the same temperature in the two because they've been in this same system, they've been in the same room for a long enough time that even if the water came out of the tap a different temperature, it is now at the same temperature as the air. And so you can see already, we had a slightly larger ice cube in this one, and it is no longer slightly larger. We're getting that ice in the water melting faster than we are the ice that is just sitting in the air. Although the one in the air is melting too, you can see that there's a little puddle forming around it. So the air condition is turning into an air and water condition, right? It's making its own water to melt in. So why is it that the water is melting an ice cube faster than the air is? Again, which is denser? Which has more particles in it per space? The air is going to be much less dense. And so just like in the CK12 simulation, where you would have the air in the oven not burning you right away, but the metal would, the water is more dense, there's more particles there, so it's able to melt the ice cube faster, even though the water and the air are the same temperature. Okay. That is our presentation on the difference between temperature and thermal energy and why you should always use an oven mitt. Okay, we're going to have a Kahoot in just a minute. And thank you for being part of us on today's Day in the Park energy presentation.
All right, guys, we will be playing another Kahoot, another energy question. I hope you guys have been paying attention to the last few sessions because we will be now testing you on different types of energy. Please join on any device, on any browser, on any device. In that browser tab, enter kahoot.it with the game pin 4668645. As soon as you enter kahoot.it into the web browser, you'll be prompted to enter a game pin. And then soon after that, you'll be prompted to randomly select a random fun username. I'll give you guys a couple minutes to join. I'll give you guys another minute to join. Again, kahoot.it on any web browser, on any device that you can imagine. Game pin 4668645. I'm very excited to see your name pop up on the screen. All right, we will be starting in 10 seconds. 3, 2, 1. Potential energy is moving energy, stored energy, no energy, mechanical energy. I'll give you guys bonus points if you guys can name whoever this is. Or, you know, the famous legend of whoever sat under an apple tree. Stored energy, potential energy is stored energy. Starting off the bat with Smart New and Mountain Puffin. If potential energy is stored energy, what is kinetic energy? Kinetic energy is moving energy. Wow, lots of people joined. Mountain Puffin taking the lead. Which of the following is an example of potential energy? We mentioned earlier that potential energy is stored energy. So which one of these is an example of it? A car driving down the street, a soccer ball stuck in a tree, paper clips moving towards a magnet, or a wound up toy spinning around in circles. It's a soccer ball stuck in a tree. It's not moving. Mountain Puffin still in the lead and is on fire, which is following an example of kinetic energy. If you remember back from question 2, kinetic energy is an example of moving energy. So which one of these is an example of that? It is when pieces of paper moves towards the charged balloon. Mount Puff is still in the lead. We're going to head into our last question here before we start our next session with Ashley. Look at the picture below. Which form of energy is present? She is winding back her bow. Is it mechanical potential, electromagnetic kinetic, gravitational kinetic, or elastic potential? The answer is elastic potential. Let's look at our leaderboard right here. Everyone has made it onto the board. Mountain Puffin, you are the winner. Thank you guys so much for playing this session. We will now be heading into our next session with Ashley. So, see you guys then.
Our final presenter of the day is Ashley Ruza. She is here to talk to us about Solar Army. She is a chemistry major at Fairmont State University. And I see on our form that Mason has already told us that he doesn't have a question, but he's excited about Solar Army. So with that, Ashley, thank you for sharing this with us today.
So as she said, I am part of the Solar Army, and I also have a little extra tidbit about hydrogen cars at the end, because I think they're really cool and they're fun to watch. And I'll just go ahead and start. Okay. So to start with, I just want to talk a little bit about what happens when you drive a car. So you have octane, which is this right here, plus oxygen. This is called a combustion reaction. And whenever they combine, you get energy to run your car, CO2, and water. So something interesting that happens whenever you have CO2, which is on this axis right here, the temperature also increases. So you can see as CO2 is increasing, the temperature is increasing. And some people say, well, that's due to ice age cycles. It happens naturally, which is partly true. If you look over here at this graphic, this is for thousands of years ago. That's the axis down here. And then concentration of CO2. So yeah, it does fluctuate naturally. But right here, around the time of the Industrial Revolution, we see a sharp increase that's farther that goes farther than it has in the past 400,000 years. And right now we're actually even above the 400 parts per million. So yeah, there are natural fluctuations in concentrations of CO2, which increases the temperature naturally, but humans are creating even more than we've ever seen. And it just keeps increasing. So this is kind of out of date where it's below 400 parts per million. We're already past that. So what the Solar Army wants to do is we want to split water using energy from the sunlight into hydrogen and oxygen. So we can use the hydrogen as fuel. So if we can do this, water and sunlight can replace gasoline, but we need something to speed that reaction up. And what we're looking for specifically is a photoelectrocatalyst. So that's a really big word, and it seems kind of scary, but you can break it down into its parts. So the photo part just means light, so sunlight. The electro just means electricity. And then the catalyst part, which is just something that speeds up a reaction. So we have some criteria for a good catalyst. It has to be non-toxic, inexpensive, and abundant. We don't want to use something like mercury or lead because we don't want to be poisoning people with our photoelectrocatalyst. And then it also has to be inexpensive and abundant. So we can't use stuff like platinum and gold because that wouldn't be accessible all around the world. That's our goal, to be able to use this everywhere, not just like rich places. So when we're testing for a photoelectrocatalyst, all of the metals that met the criteria have been tested just by themselves, and none of them have been able to do it. We've also tested 2 metals together, and again, none of them have been able to do it. So right now we're working on testing combinations of 3 metals. And if we start with these 5 metals and we combine them 3 metals at a time, there's this many combinations. And we have way more than 5 metals on this slide before that we're able to test. So we have 20 possible metals at Fairmont State, and that gives us 1,140 possible combinations. And that's not taking into account that you can do, this is just for one, like for example, 1 part copper, 1 part potassium, and 1 part nickel. You can also do like 2 parts copper, 1 part potassium, and 3 parts nickel. So there's really infinite combinations. So we have a lot of people working, trying to find a combination that can work. So here are what our samples look like. We have a little glass, we call them plates, and it's conductive on one side. That's the electro part of the photoelectrocatalyst. And then we drop something called a metal nitrate, which is just a liquid form of metal ions. So we're not actually putting metals on our samples, it's the metal ions. And then you can see right here, this little arrow is for iron standards and copper standards. A standard is just a fancy word for a control. So anytime you do an experiment, you want to have a control to compare your actual sample to. So we have iron and copper standards on all of our samples just to compare so we know if it's actually working or not. And we just put our drops of metal nitrate ratios onto the plates, and then we put them in the kiln and we're able to start testing them. So just one of the example instruments that we use to test is called SEAL, and that stands for Solar Energy Activity Laboratory. So this little black box here has LED lights, and then we put our sample down into this clear acrylic sample holder is what we call it. And then we connect these leads to our plate so we can test the electric current that's running through it. And while these lights flash, it detects a change in the electric current. So there are lights like that line up with the dots on the plate. So you have to be really careful about lining things up. And when it's flashing, it tests the current in specific areas, and we get an output that's kind of hard. You have to learn how to look at it. But what we want to see is something that does better than copper or better than iron. And that's what we're looking for. So if we find something that works better than copper or iron, our controls, then we look further into it and see if it would actually be able to split water. So with that note, we have hydrogen cars that we like to use as like little demos. So here are just some pictures of them charging over here, and then a zoomed in picture. So we have the solar panel right here plugged into something called a fuel cell, which is this blue block right here. And that becomes important later. I'll explain it. And then this is just the box that it comes in. So you can also use a battery pack instead of a solar panel. We just like to use the solar panel because it's more sustainable. So how does this work? The electric current produced by the solar panel converts water into hydrogen gas, which is H2, and oxygen gas, which is O2. And this process is called electrolysis. So it's just splitting the water into its components. And then in the fuel cell, the hydrogen gas combines with the O2, forming energy and water. So if we think back to the carbon dioxide, how octane in our regular cars makes CO2 and water and energy, this just makes water and energy. So we no longer have those carbon emissions, which increases the temperature. So here's a comparison of that. The octane and the oxygen make CO2 and water. And then if you're just using hydrogen gas and oxygen, you make water plus energy. That's just something that chemists like make it understood that it's plus energy instead of actually writing it. So I have a couple videos. These hydrogen cars take a little bit to charge. So while it was charging, I started playing with these little crickets that whenever sun hits the solar panels on their backs, they start to chirp. So I think they're really cool. They're just something fun to do while the car is charging because it takes about like 15 minutes to charge. And you know it's charging because you start seeing bubbles in these little beakers. So the solar panel, the electricity from the solar panel is splitting the water into hydrogen and oxygen. And ideally the hydrogen is supposed to go through this little tube into the fuel cell, but some of it escapes. So it's not 100% efficient. And then once it's charged, after about like 10 to 15 minutes, you can unplug the solar panel. And then you plug in the engine of the car. And this one has a switch. So I actually charged up 2 of them at the same time just so they could race. That didn't really work out, but you'll see why once the video progresses. So this one right here, it goes as soon as you plug in these leads right here. And they had trouble moving, I think because this was kind of a rough surface. The rocks right here weren't a flat surface for it to move on, so they kind of go everywhere. They didn't really want to race like I had planned. So I didn't charge them for as long as I should have because you can see because they slow down and they don't go for as long as they should be going. So in the future, I would charge them longer, but I'm impatient. And then you can see too, they have little LED lights on the little engine that light up whenever it's on. So this one died because it wasn't charged long enough. So I guess if it was technically a race, that one won, but they didn't really line up. They just kind of moved all over the place because we don't have a steering mechanism for them. They just go whichever way is easiest for them. So the rocks kind of stop them and they turn to try and go around the rocks, the path of least resistance. So these are super cool to see in person too. So these cars are just running on, all you had to do was put water in them and connect them to a solar panel. And they just use that hydrogen gas that the solar panel helps create from the water, and they start running. So it's really cool to see a car running on water, kind of. So in actual hydrogen cars, you can't have a solar panel big enough that would make enough hydrogen for an actual car to run on. So what they do is they pump hydrogen into the fuel tank like a regular car. And then there's a fuel cell that combines hydrogen and oxygen, just like it would with octane and oxygen, to make energy. The problem with current hydrogen fuel cell vehicles is that since they can't use solar panels or our photoelectrocatalysts that we're trying to find, they have to use unsustainable methods to make the hydrogen. So you can also do electrolysis with batteries. So you use the electric made from the battery to separate the water into hydrogen and oxygen. And that's just not as sustainable as it would be to use like solar energy. Because to make that electricity, you have to use a carbon source, which is going to make carbon dioxide and increase the temperature of the earth. So if we have this photoelectrocatalyst in the future, we can make hydrogen fuel cell vehicles more efficient and more earth environmentally friendly. So I have time for questions.
Yeah, to get started, I have a question for you, Ashley. How did you get involved with the Solar Army project?
So I was in Erica Harvey's Chem 1105 class, which is chemical principles for freshmen. And I was in the honors section. So we had to do a project, and I've been interested in sustainability since high school. So whenever she presented this project, I was like, I have to be a part of this. So I started with the honors class, and I've just stuck with it. I actually met my two best friends through the Solar Army with our project, and I live with them now. So it has been like a really awesome experience to get involved in.
That's kind of my follow-up question for that. I know that I've heard that being involved in clubs and things can help students stay in college and help them like have that sort of social network to support them through times that are tough and things like that. And so has being a part of Solar Army like impacted your college experience overall?
Yeah, for sure. It's nice. Like the sustainability aspect of it makes me feel like I'm actually contributing to something important that could like change the world. So that part of it helps. And then like just being involved with other people who are serious about the environment and serious about like research and stuff has helped, because it's connecting me with people that are kind of like-minded to me.
Absolutely. So are your plans to continue your education after you graduate from Fairmont State, or are you going to be looking for a job right away? Do you know what your trajectory is?
Yeah, I actually plan on going to dental school at WVU. So I really enjoy chemistry. Whenever I was starting college, the easiest way to go to dental school is get like a major in chemistry and biology. And chemistry has a lot of math, so I decided chemistry, and I enjoy it. So I really do enjoy chemistry, but I want to be a dentist. That's the end goal.
Absolutely. That's fantastic. So we have a question from Kyle. What's your favorite part about learning about energy?
My favorite part, I'd have to say just this specifically sustainable energy. I think it's really interesting how everything works. Because I've just been interested in sustainability for a long time. So particularly just how we can improve energy and make it more environmentally friendly.
Fantastic. Ashley, thank you so much for being a part of our day in the park this year. And your presentation was just fantastic. Thank you. All right. That wraps up our energy portion. We hope to see you all back this afternoon for Climate Day in the Park.